All right, so as we're in chapter 14, this is the second half that is only going to be dealing with glaciers. If you want to know more about deserts, go back and listen to the other video. So let's get started on this chapter. So as we're getting started on glaciers, a glacier is defined as snow or buildup that has begun to flow. And in order for a glacier to occur, you need areas that have more snowfall than melting. Over time, what's going to happen is that glacier is going to get thicker and thicker and thicker, and eventually it will start to flow. So again, there's a couple of different places that can occur that has more snowfall than melting. These are usually limited to either polar regions or mountainous regions at any latitude. Just like we just got done talking about with the atmosphere, the closer you are to the North Pole or the South Pole, the colder it will get. But also if you go up in altitude, the cooler it will be. And again, you just need conditions to have more snowfall than melting over a number of years, and then you're going to end up with snow that is going to build up and flow. So here's a map showing where the glaciers on Earth are currently at. Those indicated in blue, and you can see that the vast majority of glaciers are occurring at the North Pole and the South Pole, but at altitude, we also have some glaciers. So a glacier is going to start off as snow, and the snow is going to get packed together. Now, when we start looking at snow, you'll notice snow is light and fluffy. It's about 90% porosity. And again, porosity is a percentage of void space. 90% of the pore spaces are air. Now, as we also know, air is easy to constrict and squeeze together. And so over time, this snow can become more and more compacted. And as we do, we can drive some of the air out, but some of that air is going to stay in the ice. And you can end up with little tiny bubbles of air, which are really nice because they're little time capsules of the time of the air conditions in which the ice formed. And so looking at this image from your textbook, ice that is starting to get compacted is going to, the granular snow contains about 50% airspace. When the ice is compacted to firn, that's about 25% air. And then when it finally becomes this metamorphic rock, which is glacial ice, remember ice is a mineral. And so an aggregate of minerals of metamorphic rock here is this glacial ice, and it's going to contain about 20% air bubbles. So how do glaciers form? You need, well, let's see, liquid water on the Earth's surface freezes. No, that's going to create sea ice, and sea ice is very important, but it's not defined as a glacier. In order for a glacier to occur, it needs to occur on land. If we notice, we do get sea ice up in these regions, but not on water. Ocean currents can carry that ice away, and so it's not going to flow as it is going to get destroyed. Winter snow avalanches create tightly packed snow. No, because again, they're going to melt each summer, so that would not be the case. Short-term accumulations due to strong ice storms. We have strong ice storms here in Missouri, but we don't have glaciers here. Long-term snow accumulations that transform into firn and eventually glacial ice due to pressure. I think we have a winner there, as opposed to thick ice piles that form glacial ice due to the grooming of ski areas and global warming effects. Yeah, I think we're back to D. So when we start looking at glaciers, there's a couple of broad categories for glaciers. The first one that glaciers are occurring are in the mountains. And there's a lot of different types of mountain glaciers. Your book talks about mountaintop glaciers that occur at the mountaintops. In the cirques, and we'll talk about a cirque, it's a scoop, literally kind of like an amphitheater on the side of a mountain caused from glaciers. And then also valley glaciers, which are also in those mountainous regions in between individual mountaintops. And then finally, where glaciers end up moving out of the mountainous region, they're still flowing. And when they open up into these little hills, pediments, Piedmont glaciers is what they're called. So which of the following types of glaciers are formed in mountainous regions? You guessed it, all of the above. Now that's one category of glaciers, the mountain glaciers. Then we have continental glaciers. Now these only occur near the North Pole or the South Pole. Again, the North Pole, no one tells Santa, but the North Pole is in fact water. So the closest we can get to the North Pole would be up in Greenland. Now the South Pole does have land over the entire region, and so the entire mass of Antarctica is in fact covered with snow, which can build up. We have more snow falling than melting. Even being in a desert like Antarctica, a very small amount of snowfall with very little melting is going to create these large glaciers. And so we have these big continental glaciers, these continental ice sheets, these vast areas that spread thousands of kilometers across and are going to flow outward from areas of high potentiometric high pressure to areas of lower potential pressure. Now, when you look at any individual glaciers, again, if glaciers are going to move, they're going to show evidence of this movement, particularly as they're moving around. And if a glacier moves around a curve, the outer region is going to have to go a greater distance. If a glacier goes over a change in gradient, the upper region is going to move a greater distance than the lower region. And the upper part of a glacier is quite brittle, and it's going to experience what's called brittle deformation. It's going to break. Now, in our chapter on plate, on pressures, I believe it's chapter 8, we talked about plastic deformation, a mineral or a sample of material that experiences pressure, bends under pressure, and maintains the bend is plastic deformation, as opposed to elastic, which bounces back. And so when we start looking at the lower portion of a glacier, it experiences plastic deformation, but the upper region, it experiences brittle deformation. And the brittle deformation is going to yield large cracks or crevasses, which are in excess of 60 meters deep. Below that, the rocks the glacier is going to experience that plastic deformation. Now, at the bottom of the glacier, that's a tremendous amount of weight producing some extra force. And so what's going to happen is this low increased pressure is actually going to create a little surface of water right on that substrate where that glacier will move along that region. Now, again, the difference between the upper region, the brittle zone, and the plastic zone is quite pronounced right at that 60-meter line. We realize that this this difference occurs primarily when we started drilling into these glaciers. We started drilling into these glaciers, took a lot of effort, and started drilling into this borehole. And so we thought we'd be able to go down and see what's happening a little bit lower the next year. Then we put our tube in to try to monitor what has happened over the next year, and it got stuck. We now know that the lower portion of the glacier moves at different rates. Now we started looking at rivers, and we've already talked about how rivers have the banks and the bed of the river have enough friction that are going to slow the water down. And so we have this turbulent flow in a river. The same sort of thing happens in a glacier. The glacier moves at different rates. The fastest part of a glacier would be in the middle here because of that friction associated with things sticking up out of the ground, causing this glacier to get slowed down. And so what's going to happen is this lower portion of the glacier experiences this plastic flow, moving at a slower rate on the edges and the bottom of the glacier than it is in the middle. So we can actually figure out the rate at which these glaciers flow, much like the rivers, the rate at which a river flows. So where do we end up switching from brittle to plastic deformation? At 60-meter rate. Now, when we start looking at glaciers, most of the time, the first analysis when we start looking at a glacier is to try to determine the total glacier's budget. When we start looking at your account, you may start looking at how much money do I have going in, how much money do I spend, and if I bring in more than I spend, the bank account will grow. If I end up spending more than I bring in, the bank account will shrink. The same thing happens when we start looking at a glacier. When we start looking at a glacier, there's a portion of the snow of the glacier that is getting more snowfall than melting, and that's known as the zone of accumulation. That glacier will move downhill, and as that glacier is moving down, the end of the glacier will start to melt. This area, which can be quite large, identified by not being that nice white fluffy snow, being this snow that has incorporated a lot of rock, is known as the zone of ablation. And again, that's the area that has more snow removal than addition. Now we're also adding additional snow from that zone of accumulation. So if we have one area that you're adding a bunch of extra snow, one area that you're removing snow, there's going to be one point, and this is known as the equilibrium line, sometimes called the snow line, is the boundary between that has equal amounts of snowfall and melting. And that's the line separating the zone of accumulation from the zone of ablation. I have seen other textbooks call that zone of ablation the zone of wastage. And so just to realize that those terms are interchangeable. So if we started looking at a glacier, year after year after year, what's going to happen is if we had no changes, we had the exact same temperature, we had a steady state is what we call this in science, the same conditions year after year after year, more snow falling than melt, more snow falling in the zone of accumulation, more snow melting in the zone of ablation. And then the glacier would pick up materials, move the glacier material to the end of the glacier, and the glacier is going to stay in the same position year after year after year. And we always want to measure these the same time each year, because obviously if we measured it in December, it's going to have a different extent than if we were going to measure it in, say, July. And so what we're looking at is in a steady state, measuring at the same time each year, the same position of the equilibrium line and the end of the glacier are going to be the same year after year after year. But if we had more snow falling or less snow melting, what's going to happen is the equilibrium line is going to get lowered. Again, that's the boundary between areas of high, equal amounts of snowfall and melting. And if that's the case, then it's also going to push the equilibrium or the ablation line further down, and you're going to have snow at the glacier advancing. Now, most students have no problem with that one. Glacier always flows downhill. Where I've seen students having some problems is when we start talking about glacial retreat. So in this third image, what we're having here is either more snow melting or not as much snow falling. And what's going to happen is the equilibrium line will go up. Now the glacier is still moving down, but everything's going to melt out before the glacier hits the old position of the end of the glacier. And so the glacier is actually, the end of the glacier is going to get closer to the start of the glacier. And so again, materials are moving down, they're just not moving down as far. And so in this case, we'd say the glacier is retreating. And again, that does not mean it's going uphill. Gravity still works. So what's happening here is the glacier is just not going down as far. And so what do we, the zone of within a glacier characterized by a loss of ice due to sublimating or melting. Sublimation is when you go from ice to a gas without stopping in the liquid state. And so air moving over ice, you can actually turn it into a gas without, again, going into a liquid state. You need cold environments. So your freezer may have this may occur if you've ever had maybe a green bean that ends up looking like a raisin, a green raisin. What's happening there? It's the sublimation has removed the air moving over the frozen vegetable, has removed the ice, and that ice is no longer, that liquid, or excuse me, that H2O is no longer in the vegetable, and so it looks like more like a raisin. And so that is the concept of sublimation. So when we start looking at glaciers, some other kind of weird occurrences, and these can be in mountainous glaciers, or most of these are occurring in continental, but whenever we hit water. Now, when we start looking at glaciers, glaciers occur on land, but if these glaciers enter into the water, we know ice floats. And so what can happen is you can end up with tidewater glaciers. These are occurring right at the edge of the shoreline. These tidewater glaciers, again, are some areas where the ice becomes separated from the landscape depending on the tide. What can happen is this fluctuation can actually cause these glaciers, as they're advancing or retreating, but if they entering into the water, what's going to happen is these pieces of ice can break off to create an ice shelf, and the ice shelf can break off into icebergs. The process of ice breaking off is known as calving, and this calving can be quite loud. These areas can have water in the upper regions of the glacier under tremendous amounts of pressure. And so when this calving can occur, it can just break off nice and easily and create a big avalanche, a big splash of water. Can actually create a tsunami if the water is confined to these small channels. The other thing that can happen is this water pressure can actually break it forth. And so these calving glaciers can cause sizable amounts of water to enter into this region. Now, when we start looking at glaciers, the one thing that I notice when I look at an area that's been glaciated is that there's going to be some very distinct features, some very extreme features, very jagged, rough environment. Rivers tend to round things off. Glaciers, if there's something in the path of a glacier, it won't be for long. And so what's going to happen is they're going to create these glacial erosional features. Now, in Chapter 11, we looked at erosional features, are features that are caused from erosion, and the center of them are going to be usually solid rock, as opposed to depositional features where we end up with the sediments, the leftover from eroded materials further downhill. And some of the features that we're going to be looking at are things like glacial striations, or stripes or scrapes on a rock like this one, roche moutonnées, or little hills caused from glaciers passing over them, cirques, which are kind of look like amphitheaters, arêtes, which kind of look like the spine of a serrated knife, or the fish bone, like the fish spine, horns or points, and also U-shaped valleys. All of these features, hanging valleys, are examples, and fjords are examples of some of these glacial erosional features. So when a glacier moves over a region, it's going to have little bits of rock in them. And if the glacier is moving in the same direction time after time after time again, it's going to create basically indentations and grooves in the existing bedrock. We call these striations. And so we can see these striations in New York. New York's an interesting place. All of the skyscrapers in New York are built on erosional features, and it's right at the boundary between erosional features and depositional features. Those sediments that are in the depositional features, they can't handle a big skyscraper. The weight of isostasy would actually cause the sediments to dissipate out of there. And so you can't build a skyscraper on depositional features. You have to find those erosional features, those erosional features. And so that kind of dictates where you can build a skyscraper in New York, or you're going to be building flats. So when we start looking at this region, you can end up with these glaciers moving over a hillside. What's going to happen is some glacial plucking, creating this roche moutonnées, these rolling hills, where one side of the hill is experiencing this abrasion, and it's going to be scraping off these materials. Now, the backside of the glacier is actually going to the direction that doesn't have the uh, pressure of the weight of this rock going underneath there. It's going to create a little cavity. And so water can get into the pore spaces of this cavity, but it's away from that pressure. When water gets away from the pressure, it's going to freeze. We know when water freezes, it expands. And so it'll actually, this freezing will actually pluck rocks out of this roche moutonnées. And so what's going to be left behind is this plucking event, pulling these rocks off. Now, when a glacier comes through an area, the amount of erosion taking place is directly related to the proportion of the weight of the overlying material. So what's going to happen, what that means is glaciers are going to create these parabolic or U-shaped valleys, where rivers are going to cut down, and then you have mass wasting trying to create these V-shaped valleys as a result of the stability of the materials. So when you start looking at an area that's U-shaped valleys, this is going to be indicative of a glacier. And how do we know it's a U-shaped valley? Well, the bottom of the area down here does contour lines that are far apart. And as you get closer to the edges, you end up with those contour lines getting closer and closer together. So that's how I know it's a U-shaped valley. Glaciers are also going to carve out cirques. Now, a cirque gets its name from the word circus. Cirque du Soleil would be a great example of this. It's a French term that looks like this amphitheater. So what's happening here is usually these are on the north side, if we're in the northern hemisphere, where you're going to end up with more shade, more snow accumulation. And if you have more snow accumulation, you can actually start eroding that material to create these large bowls out of the glacier. And so the glacier in some cases can only be found in the cirque and start plucking and abrading. But in this case, this cirque had more snow falling than melting. And so the cirque actually is going to be the zone of accumulation for this glacier, and it's going to start flowing down this region. We can see another cirque developed over on this side. And so what's going to happen as these two glacial U-shaped valleys are moving downhill, they're going to create a ridge or a spine in between. And this is that arête. So that steep U-shaped valley in three sides is that cirque. And we can see when a contour line crosses over a glacier, it turns from that brown contour line to blue contour line, blue indicating it's ice. And so we have this cirque here associated with that contour lines. Now, if multiple cirques are coming together, what's going to happen is the center portion that has a cirque on all of these different sides, three or more cirques coming together are going to leave a point called a horn. So if in this case, these red lines are indicating different arêtes. You can see this large U-shaped valley here, this large U-shaped valley here. And so from X to X prime here is a steep region known as that arête. And we have another arête here, another arête here. And where those arêtes are coming together are these individual peaks called horns. So this is the image from your textbook showing that V-shaped valley is a result of mass wasting, downward erosion and mass wasting, creating that V-shaped valley. But if we have a glacier coming through there, it's going to carve out this material to create that U-shaped valley, create those cirques and arêtes. And if we have small tributaries going into a large river, those smaller tributaries are going to have a steeper slope. A steeper slope means it's going to erode faster. And if it erodes faster, it's going to start to flatten out. And so it's going to move very quickly, and you're going to end up with more erosion in the small tributaries than you will in the main valley. Just the opposite for a glacier. A glacier is carving out material as a response to the weight. So if you have more ice, you're going to carve down deeper. If you have a little bit of ice, you're going to have a little valley. And so where those two valleys meet it creates some interesting waterfalls where these small little tributary glaciers were hanging onto the main glacial valley. These are called hanging valleys. And so we can see a couple of these. Usually they're occupied by waterfalls in the bottom of them. We have a ret that's been shaved off by a U-shaped valley, and that's called a spur, a truncated spur. There's a couple of other glacial features that, in addition to the ones that are listed in your book, things like coals, that are all erosional features. So here's that image from your textbook showing that U-shaped valley and a hanging valley, as I just mentioned. The other glacial U-shaped valley that we need to talk about are really important from an economic standpoint, and these are fjords. Fjords are U-shaped valleys that enter into the ocean. Remember, during a time of an ice age, if we're dumping more water onto land and not putting it into the ocean, sea level will drop. Glaciers, rivers erode down to base level, and so if base level is lowered, glaciers will actually carve their way into these valleys. Sea level rises when the glaciers melt, and so we have these deep U-shaped valleys called fjords. The reason why they're very important from economic standpoint is you have really deep water really close to the earth, to the surface there. So we can go to Norway where you can have large fisheries that are in these fjords and very deep water column, and you can flush out the nutrients and the waste products from these fisheries very easily as the tides are moving the water in and out of these regions. And they're kind of confined. Here in the United States, we have big boats that unload lots of stuff here into the earth and into the United States, and then are taken off of big boats and then coming into the United States. And so if we look at places like Seattle, a big port city, it's built right on one of these fjords. Which of the following are glacially carved valleys filled with water that can be found in Norway, New Zealand, Chile, Maine, Alaska, and that's one of those fjords. I would also add Norway, Sweden, and to some of those towns or places, excuse me. So those are some of the glacial erosional features. If we look at the inside of any one of those glacial features, you're going to be hitting bedrock. Now, if we're carving out all of these materials, we got to dump it somewhere. And so these are the depositional environments where we're taking materials and putting them in a down gradient location. And if we and so the biggest difference between glacial deposits and other deposits is glaciers don't care what the size of the materials. If you'll recall from rivers, if a river slows down, it's going to dump the biggest stuff first. If a wind is blowing, it will be able to carry the clays and the silts, but not the sand. If the wind should pick up during a dust storm, you can end up picking up more of those larger grains. With a glacier, it doesn't matter. It'll dump the big stuff and the mud stuff in the exact same location. And so if it was deposited directly by glaciers with all different sizes of materials, we call that material till. Now, we call a pile of till a moraine. We start looking at these tills across Europe. We had these, we can have some reworking of these materials where the small stuff can get eroded away. And you have these big boulders in the middle of areas that shouldn't have big boulders. So these boulders are just kind of randomly placed. And so these big boulders in areas that have been glaciated are sometimes called erratics. And so that's what those terms are. We'll have glacial marine sediments, outwash loess, and glacial lake bed sediments. I'll talk about those here in just a second. So when I start looking at glaciers, in this case, we're having a glacier that is static. It's constantly picking up materials, moving them down, and if the glacier is not advancing or retreating, we're going to end up just piling up this material, melted out material out at the edge of the glacier, and this is called a moraine. In this case, it'd be a terminal moraine or an end moraine. And so that's what's happening in this glacial conveyor belt. So that is the end moraine that we just looked at. Now, in this case, we've had some glaciers. The glacier must be further up off over to where my mouse is in the left portion of the screen. But what has happened here is the glacier has retreated. And if the glacier is retreated, it's not going down as far. And so it was retreating. And as it was retreating, it was still dumping out materials. And so that is a ground moraine. It's strewn out across the ground. But if the glacier should become static again, what's going to happen is it's going to put another terminal moraine. And so we're going to call the last terminal end moraine the terminal moraine. Any other moraine that is parallel to the terminal moraine but further uphill is going to be known as an end moraine. So the end moraine is called the terminal moraine. Now, as glaciers are moving downhill, creating those U-shaped valleys, there's going to get more erosion on the sides than on the bottom. So you're going to end up with more sediments on the sides. And so what's going to happen is the end of a glacier or the sides of a glacier are going to have more material. And so this would be known as a lateral moraine. If glaciers merge, we can actually track which glacier came from what stuff, which area. This is really important. In Canada, in the last 20 years, there's been a revolution of tracking down these sediments. In particular, some of these sediments contain diamonds. And so now we can go and figure out where the kimberlite tubes are based on these moraines and looking at these sediments and figuring out how far upstream and how which direction these materials came from. These glacial materials are what we call laminar flow. They're not mixing around. They're actually in lines, and you can actually see the piles of the material in those lines. And so we've got a lateral moraine right here and a lateral moraine from a different valley. So two arêtes are carved in this region. If these glaciers should move further down, eventually those glaciers can merge, and you're going to end up with a big pile of material in the middle of the glacier called the medial moraine. Here's a topographic map looking at this glacier. And if I found a diamond right here, I can actually figure out where I want to go back and find that diamond. I can forget about this whole section if they're looking at these different moraines. What type of moraine results from two smaller glaciers merging? That would be a medial moraine. So again, this is the end moraine, big pile of material here. And as the glacier was retreating, it dumped its material here. Now this moraine can be a drainage divide. It can separate water from both directions, creates a very, very unique drainage patterns where water doesn't exactly know where to go. If you had a river valley, it can get filled in. So these moraines are glaciers are very, very effective at altering the landscape. So here's some images of some of these glacial till. And you can see this gentleman here having the big erratics in addition to this mud. Some of these erratic pieces are even larger. And so on occasion, you can end up with sedimentary, this can get lithified to become something called a tillite. Ite meaning stone of till. As the glacier is melting, as you would imagine, you're going to end up with a lot of water. And so geologists are real hesitant to use the word till. We'll just usually talk about glacial material, because to use the word till means it was deposited by the glacier and it stayed there. If it's been reworked, you're going to start separating out some of the sizes of materials. You're going to start grading it out by water and start having to go back into that river deposited materials. And so when we start looking at this, the end of a glacier, you can end up with a lot of glacial outwash water material that has been reworked a little bit, transported by streams. Water sorts this material to create these braided stream networks, and this is very, very indicative of at the end of a glacier. Again, total drainage divides have been altered, and so river deposits are totally changed. The course of the Illinois River used to not run through Peoria, Illinois. It used to be up significantly further And the glacier literally moved the river valley and filled in the one region, created a great aquifer in central Illinois called the Mahomet Aquifer, and it moved and created a different drainage pattern. Now, when we start looking at the outwash material, you have a lot of rock dust, silt-sized particles, about the consistency of baking flour. These silt particles can very easily get picked up by winds and are going to create a pile of sediment. And this pile of wind-blown sediment is called loess, and it's very, very common in areas that were deposited just south of where the rivers are, or just outside of the outwash plain. So here's some examples of some of this loess. One of the unique properties of loess is, again, it's those platy silt materials. And so what can happen is it can stack up. It has a really high angle of repose. The Peoria loess is a really classic example of this from the Illinois River. And so you can see, here's an image showing some of the different loess and the thickness of these loess. And again, these are in meters. So if we start looking, at the Iowa side of this river, on the eastern side of the river, there's a lot more loess than on the western side. Now, why is that? Oh yeah, wind flows from the west to the east. And so as a response, more loess is going to be developed in on the windward, the leeward side of this river. And notice how the glaciers did not come down. They only came down to about here. We'll talk about that if we start looking at the terminal end moraine. It only came down to here, not here in Park Hills. And so some of this loess has been transported in those locations. So when we start looking at glacial deposits, these create some lakes. And these lakes don't have, are not rivers that have wide parts of a river that have water flowing in and out. But these lakes are going to have lots and lots of water, and they don't evaporate like the playa lakes of earlier this chapter. But they can contain a lot of organic material. And as we'd expect, during the winter, a lot of that organic material will settle out. And during the summer, the organic material get taken back up. And so just like when we start looking at tree rings, we can actually see the yearly packets of organic material to lack of organic material. Just like when we start looking at those tree rings, we can count the individual years. And so here's an image. The image in the middle is a actual image of a sample of a varve under a microscope, where you can actually count those individual years and see what was happening in the past during these glacial deposits. Now, if we have a block of ice in a retreating glacier, that block of ice is not going to allow sediments to accumulate. So when the glacier melts, it's going to create a kettle. And a lot of times these lakes these depressions are filled with water. In some cases, the glacial, this cavity can be filled in with groundwater. And so these don't tend to be very deep, but they're great breeding grounds for mosquitoes. And so when we start looking at these regions, we call this topography a hummocky topography, undulating surface with lots of kettle holes and kettle lakes. And so these lakes are filled in with groundwater. Another feature associated with glacial materials are drumlins. Drumlins are sculpted from the glacier as the glacier advanced and retreated. And so you can see the streamlined nature of these drumlins sometimes look like dolphin backs. I've heard them described, where you end up with a steep side on one side and then a much more gentle location on the other side to tell us which direction the glacier was moving. Now they kind of look like roche moutonnées. The difference is these are all filled with sediment as opposed to solid rock. So here's a topographic map of these drumlins showing the direction of the glaciers were moving. In a glacier, a river, or these great glacier can have cavities, and these cavities can fill up with sediments. A river deposited material on a glacier, which when the glacier retreats, and that glacial material can be a pile of material known as an esker. Now, as a glacier is sitting on the Earth, a glacier is going to push down on all of the continental crust. Again, this is a response to isostatic rebound, something we've already covered in our chapter on plate tectonics. And so putting all this extra weight on the ice is causing the mantle to actually get pushed down. And so if we had a lake in these regions, say the Great Lakes, what can happen is the ground can actually rise back up if you remove the ice. We can actually still see to this day the glaciers causing a slight more uplift in the northern regions that had more pushing down on it than the southern regions of some of the Great Lakes. And so the shoreline actually gets altered as a response to the pushing down and pouncing back up glacial rebound of isostasy. And so when we start looking at glaciers, glaciers are really, really good at erosion, and they can totally change drainage patterns. Here's an area showing the Laurentide ice sheet, this big pile of ice that more snow fell than melting. And so what happened is the glacier advanced. And when the glacier retreated, that moraine ended up being the glacial divide, the drainage divide for this region. And you have a wall of water kind of melting out, always adding more water until one day that lake let loose. And when it did, it created havoc all across this region, created the scablands of the northwest part of the United States. When we started looking at drainage patterns, I think I've already mentioned this in a previous lecture, but we've already looked at the radial drainage patterns moving away from a point like we have in the St. Francis Mountains, indicating that we had a volcano in this region. If we had a folded strata, we're going to end up with a trellis drainage. And if we have just erosion taking place, we have a dendritic pattern. But when a glacier comes through, if it moves this material around, what's going to happen is the water doesn't know which way to go. And so it's referred to as a deranged drainage pattern. And as you can imagine, it's pretty easy to see where glaciers have occurred because these areas are going to have so deranged drainage. You're going to have tons and tons and tons of lakes, this in the kettles. And so this is why Minnesota is known as the land of 10,000 lakes. Now, when those glaciers break, again, they create huge areas. Here's an image of some of the scablands, these channels carved out of this fast-moving water, creating these huge ice dams breaking and huge torrents of water flowing down. Now, I know we've already mentioned this, but it's worth repeating. When we start looking at Peluvia Lakes are lakes that are glaciated due to increased rain. Areas formed to the south of areas that have increased rainfall. In these regions, water is moving further down. It created filled in these low-lying regions. And since that time, we're not adding additional amounts of water. And so what happens in these Peluvia lakes is these areas are drying up. The Basin and Range portion of the southwest part of the United States, the Great Salt Lake would all be examples of Peluvia lakes. Lakes that the initial injection of water was associated with the outwashing of these glaciers. So when we started looking at glaciers I've already mentioned this, but during an ice age, if you take a bunch of water and you dump it onto land and not put it back into the water, the ocean's levels are going to drop. Sea level is going to drop. And so if we start looking at sea level, during the Ice Age, during the Pleistocene time period, about 2.6 million years to 11,000 years ago, when we had periods of ice ages and then interglacials, sea level would drop and then fall and then drop and rise. And during an ice age, you would literally be able to walk from Siberia to Alaska on land. And so looking at this region, we can actually, anthropologists have been able to track human civilization across into North America at about the same time that this ice age occurred. Coincidentally, that's also the same time that we started seeing some species or some organisms going extinct. And so this is the, again, Pleistocene. We already talked about this in chapter 11, but as a reminder, the Pleistocene is the time period that had these ice ages. Extending to the south, now here in Park Hills, we did not experience the direct effects of a glacier. We had a lot of outwash, we had loess deposits, but further north up, right around St. Louis, we did have we had the Termalic Glacier associated with them, with the last ice age. And the animals also had to accommodate this lack of vegetation. So they were also altered and moved further south. And so animals like the mastodon, the giant sloth, were moving around, and we were able to determine by looking at a Clovis point that was in that humans were able to go and track these mastodons, get them to go into a sinkhole, which you could have your the elevation advantage, and have mastodon burgers. You could eat these, you could consume these mastodons and have a lot of food for one tribe, one group of people. And so when we started looking at the life associated with these mastodons and mammoths and giant sloths, and so the life on North American continent was quite a bit different than it is today. We also had the short-faced bears, and I'm kind of glad that they went extinct personally. But we see evidence of these in this region. This is why the Southeast Missouri or Missouri State bears exist as a result of the mascot that's directly related to this glaciation. So when we start looking at the geological record, we can see that we've had some fluctuations, that we had times of ice ages and interglacials. The most recent ice age was called the Wisconsin glaciation, and we're in this interglacial time period right here. And so if we go back, we had cooler environments based on the oxygen isotopes. What we're looking at here is during an ice age, we're taking more of the light water and we're dumping it on land in ice. And so that means that the oxygen 18 is going to be in the water more, and in the shell fragments that are using those oxygen. The oxygen on the land is going to be more oxygen 16. And so we can see during an ice age, we had more oxygen 16 on land and more oxygen 18 in the water. And during a interglacial, we melt out the ice and we increase the oxygen 16 in the oceans and decrease the oxygen 16 concentrations on the Earth. And so that's how we're using the oxygen isotopes here on the landscape. And so the last ice age was the Wisconsin. The Illinoisan was the most extent. It went down to here. And so you can see that the Wisconsin was not as far. Now, if we had a glaciation that occurred before that, and it looks like based on the oxygen records that we did, what would happen is the glacier, when it advanced, it would destroy any of the previous evidence of the previous glaciation. So what epoch did the most of the recent ice age occur in? I think I've mentioned this 3 times now, is the Pleistocene. When we start looking at other ice ages, and again, these ice ages are directly linked to Milankovitch cycles. More on that in chapter 10 if you need a refresher. So when we start looking at other ice ages, we can look in the geologic record, and we've already mentioned we've had some snowball Earth at the end of the late Paleozoic, the Proterozoic. We had some cooler environments indicated by one of these ice ages. And some of these are very, very rapid, abrupt changes. So we start looking at the ice ages. Again, if we have more land masses near the North Pole and the South Pole, that's going to allow more snow to build up and create a larger snow. And if we have more snow, then we're going to end up with more sunlight's going to get reflected off the Earth, and that can drop the temperature, which is going to precipitate more of a longer range ice age. Another big change is if we were to get rid of some of the concentrations of carbon dioxide in the atmosphere. We know carbon dioxide is a greenhouse gas. And so if we took all the carbon dioxide out of the atmosphere and dumped it into rock, and like a limestone that has carbon dioxide in it, what would happen is the temperature would drop. In fact, we're looking at some different ways to sequester carbon dioxide in limestone like that. These days, we haven't been able to find a way to do it effectively, inexpensively, but that is one of the ways. And you hear about carbon dioxide sequestering. That's one of the things that they're looking at doing. But when we start looking at short-term ice age interglacial, these are going to be associated with Milankovitch cycles. And so, again, we talked about this. These are for, orbital variations, and there's 3 of these orbital variations. One is the ellipse, the orbit in which the Earth moves to become more rounded to ellipse, rounded to ellipse, rounded to ellipse. The tilt of the Earth, associated from 23.5 degrees to 22.5 to 24.5. And then the wobble of the Earth, whether the Earth's, we know that the Earth's axis is pointed towards the sun. The North Pole is tilted towards the sun when we're furthest away from the sun, when we're up here in the aphelion. And the Northern Hemisphere has a lot more land on it than the Southern Hemisphere. If this were to switch, if the wobble was pointed towards the sun, when we're closest to the sun, this would have a really big impact on the temperature. And so when we start looking at Milankovitch cycles and the effects of these Milankovitch cycles, they match nicely with the ice age to interglacial ratios. And so these are all short-term variations, again, of those Milankovitch cycles, all 3 of them. So when we start looking at this chapter, if you have any questions, be sure to let me know. Have a great day.